Hey there guys, how's it going? Mike coming back at you here with another video on Calculus 1. In the previous video, we gave you an introduction into optimization problems. We went through the 6-step process that you need to do every time you get an optimization problem, and we went through one sample problem to see how we do these kinds of guys. In this video, we're going to do a couple more problems here using that same process, and these problems are going to be a little bit more challenging, just a little bit more involved. So next problem up here, it says a rectangular box with square base and no top is to be constructed such that the volume is 100 cubic feet. So this is a very big box that we're building here. Find the dimensions that will minimize the amount of material needed to make the box. So step one, we said draw a picture if the given type of problem calls for it. So this is my sketch of a rectangular box. Not the best thing, but that's why I majored in math, not art. So it has a square base and no top. Now, the square base comes into play in both the objective and the constraint equations. The fact that it has no top really only comes into the constraints, or into the objective, sorry, and we will see that shortly. Now, typically a box would have length, width, and height that don't necessarily have to be the same. But because the question specified that this is a square base, we know that the length and the width are going to be the same value. So I call the length and thus the width x, and my height y. You could have used L and H or W and H, or really just whatever you wanted to use. But that's the sketch of my rectangular box there on the left-hand side. Going back to the statement of our question, it says that the volume is 100 cubic feet. So we're told that volume has to equal some fixed quantity. It has to equal some fixed constant. So a quantity equaling some fixed constant tells us that that is what's going to be our constraint equation. So we know that our constraint is going to be 100 equals, and we know that it's our volume. The volume of our box, volume of a rectangular box, is length times width times height, or in this case, x squared times y, x times y. The objective that we have to hold to, the question says find the dimensions that will minimize the amount of material needed to make the box. Now this is a little bit tricky, but saying that the amount of material needed to make the box means that we're minimizing the surface area of this rectangular box. So we're going to minimize the surface area. So let's come up with an equation for the total surface area for this box that we have to build. Typically the box would have 6 sides to it, the top, the bottom, and then the 4 outward facing sides. But the question said that this box has no top. So we don't need to worry about the area of the top. We just need to worry about the area of the bottom and the 4 outward facing sides. So the area of the bottom, or the area of the base, length is x, width is x. So the area, and this is the total area, is going to be the area of the bottom, which is x squared, plus, now this problem is nicer in the sense that the areas of each of our 4 outward-facing sides are all going to be the same thing. For each of our 4 outward-facing sides, the length is x and the height is y. So we have x times y on the front-facing panel, x times y on both side-facing panels, and then x times y on the backward-facing panel. So we have xy plus xy plus xy plus xy, or plus 4xy. So these are our objective and our constraint equations. As we said in the previous video, this is the one step that you have to make sure you get properly. You have to make sure that you come up with the correct objective and constraint equations. If you don't, then the problem is going to fall apart from here. You may be able to use our process, our whole 6-step process, but you're not going to come to the right answer. So, next step, we have to take our constraint equation and we have to solve it for one variable in terms of the other. Now, looking at this equation right here, overall, it's going to be a lot nicer if I get y in terms of x as opposed to getting x in terms of y. If I get x in terms of y, I'm going to have square roots in there, and that's just not as fun to work with. So if I just divide both sides by x squared, y is equal to 100 divided by x squared. Then I take this result, which I just found, and I substitute it into my objective equation. So 100 divided by x squared is going to take the place of the y that we have here. So area is now x squared plus 4x times 100 over x squared. Let's simplify this guy out. Let's cancel some things. The x squared still remains the same. We have an x on the top and an x squared on the bottom, so we can cancel out one of the x's. So we're just left with one x on the bottom, and then we have a 4 times a 100 for a 400. Now that we've simplified that out, next step, we differentiate, we set equal to 0, and we solve for x. So the derivative here, a prime, 2x, and then 400 divided by x is the same thing as 400 times x to the power negative 1. So when you differentiate, you're going to get a negative 400 divided by x squared. Set this equal to 0. We find that 2x is equal to 400 over x squared. We can multiply both sides by the x squared. And we get 2x cubed is equal to 400. And then from here on out, it's not too complicated. Divide both sides by 2 and take the cube root. And if we plug this into our calculators, we find that we come up with rounded to 3 decimal places, we get 5.848. And this was, we were talking about our volume in cubic feet, so this is feet we're talking here. and this was our x value. So we've solved for one of our unknown values. Next thing we're going to do is we are going to take this x value that we found, and we're going to substitute it into our constraint equation. We found that y was equal to 100 over x squared. So y is equal to 100 divided by 5.848 squared. If we do 5.848 times 5.848, we get just over 34.199104. So if we do 100 divided by that, we get just under 3. We get about 2.924. And that is our other value that we were looking for. That's the value of our other unknown. So last up, answer the question that was posed to us. The question said, find the dimensions that will minimize the amount of material needed to make the box. We're not looking for the actual area, we're just looking for the dimensions in this case that will minimize the amount of material needed. So we had our length and width as 5.848. Feet by 5.848 feet by 2.924 feet. And there we go. That is our final answer. This is what we are looking for right here. So you can see that we went through each of our 6 steps when going through this particular problem here. Next problem, we wish to construct a cylindrical can with a bottom and no top, and the can must have a volume of 30 cubic centimeters. Determine the dimensions of the can that will minimize the amount, minimize the surface area of the can. Use the fact that the volume for a cylinder is pi r squared h, and that the surface area for this particular cylinder is going to be 2 pi r h plus pi r squared. So it's a very, very, very similar problem, except we are doing a cylindrical can this time instead of a rectangular box. These types of problems, just on a quick side note, where we fix one of volume or surface area and we have to minimize or maximize the other one, these do make for very good problems. They're not too challenging, but just a little bit of a challenge just to help us out here. So I'm going to pause, I'm going to take a little break here, pause the video, try this problem on your own. Try to come up with a sketch, come up with your objective and constraint equations, go through the whole process, and let's see what we come up with. When you hit play, we'll go back through this problem and see what the answer is. Okay, guys, so let's see what you got when you went through this problem. Again, this is a problem where we can sketch a picture. So here's the sketch of my cylindrical can here. We have our radius r and our height h. The question told us that the can had to have a particular volume, so we're going to take the volume formula that we were given, and we were going to set it to we're going to say equal to that volume of 30. So our constraint is going to be 30 equals pi r squared h. And we had to find the dimensions that will minimize the surface area, and we were given the surface area for this particular cylindrical can in the question. Certain shapes you may have to know what the formula for the volume and the formula for the surface area are. Some shapes you won't have to. So our area, 2 pi RH plus pi r squared. So we have our objective and our constraint equations. We're going to kick it off by taking our constraint equation and solving for one variable in terms of the other. Again, looking at this, we could solve for r in terms of h, or we could solve for h in terms of r. I'm going to choose to solve for h in terms of r because we're going to see that it's going to turn out to be a lot nicer. So if we divide both sides of that equation by pi times r squared, we find that h equals 30 divided by pi r squared. We substitute this into our objective equation. We're going to find that area is 2 pi r times rh, which is 30 divided by pi r squared plus pi r squared. And when you look at our first term there, we have a pi and an r that we can cancel out from the top and bottom. So we're left with 2 times 30, or 60, divided by r. And then plus pi r squared. We now have this in terms of one variable. We take the derivative, we set it equal to 0, and we're going to solve for our unknown r. The derivative of 60 over r minus 60 divided by r squared plus 2 pi r. Set this equal to 0 and solve for r. We can add the 60 over r squared onto both sides. Multiply both sides by the r squared. And then we can divide both sides by 2 pi and then take the cube root. So r is equal to the cube root of 30 divided by pi. And if you plug this into your calculator and round to 3 decimal places, you get 2.122. And the question said that our volume was in cubic centimeters. So the unit of measure here is going to be centimeters. We're going to take this r value that we found. We're going to take that, we're going to substitute it into our constraint equation. We had h is equal to 30 over pi r squared. So this means h is 30 divided by pi times 2.122 squared. And if you plug this into your calculator and round to 3 decimal places, you get approximately 2.121 centimeters. So Radius and height, almost identically the same thing. Now, be sure to answer the question that we were posed. The question said, determine the dimensions of the can that will minimize the surface area. Again, we're not being asked to find what that minimum surface area is. So we can just say radius, 2.122 centimeters. Height, 2.121 centimeters. And there we go. That is the end of our second and last problem here for this video. So the big thing to be sure that you get down is that 6-step process that we talked about in our previous video. If you understand and memorize and follow those 6 steps, again, keeping in mind that step number 2 is the most critical. If you get past number 2 and follow those other 4 proceeding steps, then you'll have no trouble with solving optimization problems. If you have any questions or comments, be sure to leave them in the comment section below. Otherwise, until the next video, take it easy.